Welcome to Lecture 18. I misspoke the last time in Lecture 17 when I said today we're going to be looking at hydrogen in an electric field. It's actually hydrogen in a magnetic field that we're looking at. And we're going to be thinking at the moment about the magnetic field being small in the sense that the splittings that we're getting from the magnetic field will be smaller than the fine structure splittings that we have obtained in the last lecture. So we're going to break the problem into two steps. We're first going to solve for the fine structure, and then we're going to perturb the fine structure due to the presence of the magnetic field. Now, this weak field regime is called the Zeeman regime. In the other situation where the magnetic field is large and we can treat the fine structure as a small perturbation relative to the magnetic field, that's called the Paschen-Bach regime. We're going to solve the general case assuming that we actually have no fine structure and no magnetic field first, and then figure out how do we do that degenerate perturbation theory. So we have an orbital magnetic moment of the electron, which is given by minus mu dot L, where mu is equal to EH bar over 2mc. We're using this normalization requirement from Gottfried, where the angular momentum is dimensionless and the h bar comes out and goes into the constants like mu zero. That's called the Bohr magneton, and it has a value of 0.579 times 10 to the minus 8 electron volts per Gauss. Now you should recognize that that's a pretty small number. So a big magnetic field like a Tesla, I think, is 10 to the 5 Gauss. Even a big magnetic field is going to cause energy levels to shift no more than the order of 10 to the minus 4 electron volts. And since the energy levels of hydrogen are, on the order of 10 electron volts, that's a really tiny shift. As you recall, the shifts in energy due to the fine structure were on the order of 10 to the minus 4 electron volts. So if I use just a normal ordinary magnet, maybe one that's 1,000 Gauss, these shifts are going to be quite small, okay? The spin magnetic moment is the same mu zero, minus 2 mu zero times S, and that 2 is that Thomas precession factor. It's that factor of 2 that makes life rather difficult in the way in which we solve these problems, and that's because the magnetic perturbation is mu zero magnetic field dot L plus 2S. Which we can write as mu zero h dot j plus s. Now we know that if we take the magnetic field in the z direction, then that would be mu zero h jz plus sz. Now, if we work in the coupled basis, which we have to work in for the fine structure because those were the parallel direction, we're working with j squared, jz, l squared, and s squared. And in that case, Jz is a good quantum number, but Sz is not. And so it will mix different components. On the other hand, if we worked with the uncoupled basis, the S squared, L squared, Lz, and Sz, they all commute with V mag. And so we could actually work out the perturbation theory. We know what all of the parallel directions are immediately. We work out all the perturbation theory in that basis. But then the fine structure becomes non-diagonal. So we want to work in a situation where the fine structure is going to be diagonal and the magnetic field effects are going to be potentially non-diagonal. So the field will mix states, the fine structure states, when they're coupled by the SZ operator. Okay? Now, an important thing to note is LZ plus 2SZ is an even parity operator. Now, again, I get the parity by changing the signs of x and changing the signs of p. Obviously LZ, because it involves an x cross p, that does not change when I change the sign of both x and p. And SZ, which doesn't depend at all on x or p, doesn't change sign either. So this is an even operator under that parity operation. And that means that it can only connect it cannot connect states with different parity. It can only connect states with the same parity. And again, I want you to be clear on this because students do have trouble with this. parity is determined by the L angular momentum. When L is even, it's an even parity state. When L is odd, it's an odd parity state. This means that the perturbation that we're putting on can only couple states that have the same parity. That means L must be the same or differ by a multiple of 2. In particular, I cannot connect S states to P states. Okay, now let's go through our counting. So if you don't like the spectroscopic notation, just remember there are 3 P states and 2 spin states. So there's a total of 6 P states when I take spin into account, and there's 1 S state but 2 spin states. So there's a total of 2 S states. That's a total of 8 states. If we look instead with the spectroscopic notation, 2P 3/2, that J is equal to 3/2. I have 2J plus 1 or 4 states. I have a 2P 1/2 and a 2S 1/2. Each of those have J equals 1/2. Each of those have 2 states. And so I have 4 plus 2 plus 2, which is 8 states. So there are 8 degenerate energy levels when I do not take into account fine structure or the magnetic field effect. But the parity argument tells us that the 2S 1/2 cannot couple to the 2P 3/2 or the 2P 1/2 because S is a parallel direction. Similarly, the 2P 3/2 cannot couple because JZ is a good quantum number, since LZ plus SZ commutes with the Hamiltonian, and that means that the LZ plus SZ, because there's only one way of forming M equals plus or minus 3/2, the expectation value of the SZ is known. Okay? That's another way of thinking of it. So those guys also don't couple to anything. It's the 2P 3/2 M equals 1/2 and the 2P 1/2 M equals 1/2 that couple. And it's the 2P 3/2 M equals minus 1/2 and the 2P 1/2 M equals minus 1/2 that couple. So those are the two that couple together. And so what we've done now is we've taken an 8x8 degenerate perturbation theory problem and we've reduced it into 4 1x1 problems. Those can all be treated with non-degenerate perturbation theory, and 2 2x2 problems, which we have to construct the 2x2 matrices to find the eigenvalues for. All right, so we're going to first work with the 1x1 subspaces because we can use non-degenerate perturbation theory. And that means to first order, the shift in the energy is just given by the matrix element, the V00, which means I just look at the expectation value of N L J M JZ plus SZ N L J M times mu 0 H. Now JZ, it's an eigenvalue. It's given by M. So that term just comes out. I get mu 0 H M plus NLJM SZ NLJM, and we have to figure out what that overlap is. Now, when I look at the overlap, I have angular momentum states and I have radial states. Because the states are the same, the radial part of the overlap is going to just give me 1. The angular momentum piece is more complicated, and we have to work that out carefully. The way that we do that is we are going to be working with a basis where the SZ is an eigenstate. So that's the basis that involves L squared S squared LZ SZ. And in order to convert this state that we have, the LJM state, into the LLZ SZ basis, in order to convert to that, I need to use the Clebsch-Gordan coefficients. Now, what's nice is when the SZ acts in that basis, its eigenvalue is given by MS. So what we're going to find is, with the way those Clebsch-Gordan coefficients work, is I just have to sum over all MLs and all MSs that are in my given representation, the value of MS multiplied by this probability, the overlap SLJM with LMLSMS, modulus squared, which is the square of the Clebsch-Gordan coefficient. Now, because these states are angular momentum states that I got by combining L equals 1 with L equals with S equals 1/2 to get my total J, we know the Clebsch-Gordan coefficients. We work those out in lecture, and I'm writing them down again for you here. The L plus 1/2, so that's J equals L plus 1/2 M state, had these coefficients, square root of L plus M plus 1/2 over 2L plus 1 times the state that has ML equals M minus 1/2, MS equals 1/2 plus square root of L minus M plus 1/2 over 2L plus 1, ML equals M plus 1/2, MS equals minus 1/2. And then in the case where I have j equals L minus a half, we have these other two coefficients. Okay, so let's work with the case j equals L plus a half. In that case, when we do the calculation, that first term gets squared. That's going to give me an L plus m plus a half over 2L plus 1. And the expectation value of ms for that state is equal to plus 1/2. So that gets multiplied by plus 1/2. And then the second term, I square that coefficient. I get L minus m plus a half over 2L plus 1. But the expectation value of ms there is minus a half. So I get a minus 1/2 there. And now we just have to combine these together. You see the L's will cancel, the halves will cancel, but the m's will add together. And we end up with m over 2L plus 1. That's it. We got the expectation value. Now we do the same thing with j equals L minus a half. We'll get a half, and then we have to square that first guy. That'll be L minus m plus a half over 2L plus 1. And we get a minus 1/2 times that L plus m plus a half over 2L plus 1. When we add those two guys together, this time we get a minus m over 2L plus 1. Okay, that's it. We got those expectation values. So now we can summarize what we're going to get when we put that together with the result that we had before. The result we had before was an m. So I now have to add an m plus or minus m over 2L plus 1. You see I can factor the m out of that, and what I'm going to get is I'm going to get 2L plus 1 plus or minus 1 over 2L plus 1. So now we're going to go back and we're going to construct now the full shifts in the energies. So we have to go back and look up what we did for the fine structure in the last lecture. So the shift in energy due to the fine structure was given by E0n alpha squared over n squared multiplied by n over j plus a half minus 3/4. Now when we look at the state 2p 3 halves m equals plus or minus 3 halves, the n value is equal to 2. The j value is equal to 3 halves. So you see that's going to give me a 1. I'll get 1 minus 3/4 or 1/4. And then I have to add in the result that we got. Well, if it's a plus 3 halves, then the m is equal to plus 3 halves. My L, in this case, it's a p state. So the L is equal to 1. So I will get 2 times 1 plus 1. And in this case, we're looking at the case that is j is equal to L plus a half. So I'm going to add the 1 to that. So I'll get 4 over 3 for that last combination. You see the 3's will cancel. I can divide out a 2, and I'm going to end up with E02 times alpha squared over 16 plus or minus 2 mu 0 h. We've now gotten that plus or minus 2 mu 0 h, with a plus or minus coming from the fact that the m is plus 3 halves or minus 3 halves. Now we do the same thing for the s. The fine structure term is going to give me, because in this case it is j is equal to 1/2. I will have a 2, but I'll have a 1/2 plus a half, so that's going to give me a net of a 2. And then 2 minus 3/4 is going to give me 5/4. So we'll get E02 times alpha squared over 4 times 5/4. And then I'll get plus or minus, in this case, my m is plus or minus a half. And my L is equal to 0. So, and my j here is equal to L plus a half. So I'll use the plus sign. So I'll get a 2 divided by 1. So I get mu 0 h times a half times 2 with a plus or minus sign. So we get E02 times 5/16 alpha squared plus or minus mu 0 h. And we've gotten now 4 of our energy levels done. So that's pretty neat. It shows you that if you carefully work through and think about what overlaps with what and so forth, you can greatly reduce your work. Because the other way of doing it, we have to calculate an 8x8 matrix, which is 64 matrix elements. And we have to then find all of the eigenvalues of an 8x8 matrix, which is not something that you could easily do by hand. Okay? All right. We now have 2 2x2 cases we have to work out, and these get a little bit harder. We're going to first work out those diagonal fine structure matrix elements because we're working in the basis where the fine structure is diagonal. They're going to be alpha squared E0 over 2 divided by 4. In the case where I'm looking at the p states, it will be 2 over 2 minus 3/4, which is going to give me E0 2 over 16 times alpha squared. That's for the case when j is equal to 3 halves. That's the case where it's the p state and it is the j equals L plus a half. And then when I look at the p state when j is equal to 1/2, that's going to be the same prefactor, but it's going to be a 2 divided by 1 because the j plus a half will equal 1 here. And then it's going to be minus 3/4, and we'll get 5/16 E02 times alpha squared. So those are the diagonal matrix elements of the 2 by 2 matrix. The diagonal magnetic matrix elements are coming from the exact same calculation that we already did, because you can view the calculation we did before with the JZ plus SZ was the diagonal matrix element. So we just plug into that formula that we had, and we're actually going to get the same results that we got before for the j equals 3/2, except the m value now is going to be plus or minus 1/2 as opposed to plus or minus 3/2. So we're going to get a slight change in that calculation. And we had not done the case with the p state that has the 1/2. So you have to go through and do that calculation. The L is equal to 1, but now we're going to use the minus sign because it's j equals L minus 1/2. And you find that you're going to get, in that case, a 1 plus or minus 1/3 mu 0 h. Okay, so those are the diagonal terms. So our total diagonal terms are going to be the sum of the contribution from the fine structure and the diagonal term from the magnetic matrix elements. And we still have to now calculate the off-diagonal matrix elements. Again, we have to go to the Clebsch-Gordan coefficients in order to do this. Now we're not going to get a square of the coefficients because the two coefficients are going to correspond to different terms. But when we go into this basis, the SZ operator, it's an eigenstate of the SZ operator, so we can pull that eigenvalue out. That's going to give me the m sub s. And then we have the product of these two terms, a term that is s equals 1/2, L equals 1, j equals 1/2 m, with s equals 1/2, L equals 1 ml ms, and s equals 1/2, L equals 1 ml ms, with s equals 1/2, L equals 1, j equals 3/2 m. Now, when we go through this, we're going to find only 2 ml values contribute. That's always the case when I'm adding a spin 1/2 to something. There's only 2 ml values that contribute. We have to go back to our table and find what each of these coefficients are. And there are 2 different coefficients that we're multiplying together. We have to be careful about signs as well. We have to remember we're working with the case where L is equal to, j is equal to L minus 1/2 when it's a j equals 1/2 state. And when it is the j equals 3/2 state, we have to work with the case where j is equal to L plus 1/2. So we get those 2 different coefficients that we multiplied together. They're shown there for you, and we have the plus 1/2 and the minus 1/2 for the ms, depending upon which term we're working on. So now we have a little bit of algebra. We have to multiply those terms out. You actually can see that those 2 terms are the same. They're both equal to L plus 1/2 squared minus m squared. The denominators are equal to 1 over 2L plus 1. And because of the way the signs work, we get a minus 1/2, which is just going to give me a minus 1 for the case where m is equal to plus or minus 1/2 and L is equal to 1. So we plug in L equals 1 into that. That L plus 1/2 will give me a 3/2. That'll, when I square it, that's 9/4. 9/4 minus 1/4 is 8/4, which is just equal to 2. So I'll get a square root of 2. So we get minus square root of 2 over 3 for the m equals plus or minus 1/2. This means our first matrix element is going to be a minus square root of 2 over 3. And it's the same matrix element whether m is equal to plus 1/2 or m is equal to minus 1/2. Okay? That then allows us to plug in and get our 2 by 2 matrix. And again, we have the diagonal terms coming from the fine structure, alpha squared E0 2 over 16 plus or minus 2/3 mu 0 h. I'm going to subtract an epsilon because I want to get the eigenvalues. Off diagonal terms are minus mu 0 h root 2 over 3. And then the lower diagonal term is 5 alpha squared E0 2 over 16 plus or minus 1/3 mu 0 h minus epsilon. So now I have to calculate that determinant. It's going to give me a quadratic equation in epsilon. The algebra gets a little bit messy, but you can do it pretty carefully and straightforwardly. We get an epsilon squared term. The coefficient of the epsilon term is minus the trace, so we just have to add those 2 guys together. I get a 5/16 plus a 1/16, that's 6/16, which is equal to 3/8. So I get a 3/8 alpha squared E0 2. And then I will get a plus or minus 2/3 plus 1/3. That's plus or minus 1. So I'll get plus or minus mu 0 h. That's times epsilon. And then I have to calculate the determinant of the matrix to get the remaining constant term. So I have to multiply out those diagonal terms. I'll get a 5 alpha to the 4th E02 squared divided by 256. I will get a plus or minus 11 over 48 alpha squared E02 mu 0 H. And then when we look at the terms that involve the H squared, I'm going to get a plus 2/9 mu 0 squared H squared, but then I'm going to get minus the product of the diagonal terms. But if you look at those, that's going to be minus mu 0 squared H squared times 2/9. So those guys actually cancel. The H squared terms cancel, and I'm left just with the linear term. Now it's a quadratic formula. We just plug into our equation. We're going to get 3/16 alpha squared E02 plus or minus 1/2 mu 0 H. And then we're going to get plus or minus 1/2 the square root. I have to square that term. So I'm going to get the 3/8 is going to get squared and give me 9/64. And then that 9/64 is going to be, we're going to be subtracting from the 9/64. We're going to be subtracting 5 over 64. So 9 minus 5 is equal to 4. So I get 4 over 64, which is 1/16. So that's why you have a 1/16 alpha to the 4th E0 squared there. When we look at the cross terms from the summation, we're going to get a plus or minus 3/4 from the square of the term that multiplies the epsilon, plus or minus 3/4, and then we're going to be subtracting minus plus 11/12. Okay, well, 3/4, that's 9/12 minus 11/12 is 2/12 or 1/6, and it's going to be a minus plus 1/6 times that alpha squared E0 squared mu 0 H. And then I just take the square of the H term from the coefficient of the epsilon. That's a mu 0 squared H squared. Now I want to carefully point out the plus or minus signs that are pointed to from below. Those signs correspond to whether or not mj is equal to plus or minus 1/2. The plus or minus sign in front of the square root, that corresponds to the 2 roots of the 2x2 equation. Okay? Now we have to plug in the situation in the case where mj is equal to plus 1/2. So I'm going to take plus for those 2 roots that are pointed out from below. And we get 3/16 alpha squared E02 plus 1/2 mu 0 H plus or minus 1/2 this square root of this ugly term. If we go ahead and we look at the case where mj is equal to minus 1/2, we'll get that 3/16 alpha squared E02 minus 1/2 mu 0 H plus or minus 1/2 that nasty square root that now has a plus sign instead of a minus sign inside it. To work out the small h limit, the Zeeman limit, and another way of saying this is to figure out what it looks like as a function of h, what the linear and h term corrections are. We have to do an expansion of that square root. So we have to factor out the 1/16 alpha to the 4th E0 squared from it and then do an expansion of the square root. It's a fairly straightforward exercise. Again, lots of opportunities to make mistakes, but if you do it carefully, you ultimately get that the 2 roots are going to be given by this 3/16 alpha squared E02 plus or minus 1/8 alpha squared E02 plus 1/2 mu 0 H plus or minus 1/8 alpha squared E02 times this complex combination of numbers, minus 16 over 6 mu 0 H over alpha squared E02 times 1/2. And when all the dust settles, when you take into account those plus or minus signs, you'll get a 5/16 alpha squared E02 plus 1/3 mu 0 H, and you'll get a 1/16 alpha squared E02 plus 2/3 mu 0 H. And you can see that 5/16 and 1/16, that is the correct result for the fine structure. So we did our expansion correctly. You do the same thing with the mj equals minus 1/2, and you find that you get the 5/16 minus 1/3 mu 0 H, and you get the 1/16 minus 2/3 mu 0 H. Okay, so that's what we would get in the small h limit. The large h limit, that's when h dominates over everything else. You can just take a look at the square root of plus or minus 1/2 the square root of mu 0 H coming from that quadratic. And that means that we're going to get shifts that when mj is equal to plus a half that correspond to mu 0, h, or 0. And when mj is equal to minus a half, it'll be minus mu 0, h, or 0. Interestingly, in this high h limit, not all of the degeneracy ends up getting lifted. Okay? And you can think of those terms as being effectively independently jz plus sc, which we can think of as being independent of each other in the limit where the h is very large, because it's going to pick out just one of those two as being the important one in the contributions that we are summing over to get these energy differences. Okay, that now is the end of lecture 18. We have gone through our first non-trivial degenerate perturbation theory problem. It was not so bad because the first order matrix that we had to calculate in order to determine the directions that the perturbations went in was just 2x2 matrices. In the general case, you will have to work with more complicated cases than just 2x2 matrices, and you will have some opportunities to look at examples that will come out this way in the homework. But for now, this is all that we have for this lecture, so I'm going to end lecture 18, and we'll see you again in lecture 19.